same.
The first part was okay.
The first problem was
The
not
second
bad.
problem is mostly sketchy, isn't it?
And then finding the
That's what I
analytic
thought.
angular
So it's mostly
momentum.
sketchy, and the sketchy isn't super difficult. And then the first one just ends up being like, it's like the weird ellipses, yeah.
M part? With the exam.
Well, that one's just sketchy too, isn't it?
And parts. With the exam.
Okay, today we're continuing our development of the orbital dynamics. We mostly looked at the Rutherford scattering in the last lecture and just began to see what the orbits would be like in general. And this particular front page and also inside this lecture are clickable links. So if you have the PDF or Keynote version of this thing, you can look at these old papers that we put together. And most of these were put together in connection with a class like this one. And maybe someday we'll get to the point where we actually write a paper in this class. That hasn't happened at this university, but you might be enjoy reading just the very much simpler explanation, I think, than or simpler examples. Today we're going to take some fairly complicated ones, and plus this is something that isn't in those papers. The relationship between the ratio parameter, the ratio of your kinetic energy to your potential energy, sort of a weird thing in mechanics to do that, but it really helps in this case. And then the launch angle, that, and then the epsilon lambda parameters, what we consider as the polar coordinate parameters of lattice radius and eccentricity. And then just the good old Cartesian parameters of major radius and minor radius, A and B. So playing those against each other lets you solve some problems that are fairly tricky otherwise. They're pretty tricky this way too, but it's an improvement. So we'll be going over some pretty fast. I'm going to, scoot through this fairly quickly just to spend a whole lecture on things like this. I want to get to some other more physical topics than just the intricate work that it takes to do a complete geometrical construction of an orbit or family thereof. So let's go ahead and do the review of what we have already discussed, and I'll try to keep these two screens in sync so that we can play the animations. There are quite a few that we have to show for these three different cases, but not only these three different cases, but also families of orbits that involve these three different cases, just to refresh your memory. Now, one of the things that I really want to emphasize, of course, is that beyond this course lies the quantum mechanics and the symmetry of quantum mechanics, and the idea that this eccentricity vector, this vector that's made of, and I see got the old font problem with a little hat that should be on top of the R. This is a unit vector as indicated here by the vector divided by its magnitude, the radius. In any case, this vector that's made out of this curious combinations of momentum, position, and the constants of mass and the Coulomb repulsion constant or retraction constant. That vector is analogous, as I mentioned briefly when we introduced it in the last lecture. It is in some ways related to the Stokes approach, the Stokes vector, in fact, the spin vector that we use to describe the harmonic oscillator, in isotropic harmonic oscillator orbits. Of course, the real use of this was when the thing was not isotropic and we had various asymmetries or bilateral shapes, or worst of all, or most interesting of all, the cyclic or Coriolis or circular perturbations, or all three together. So far, this has not developed enough that we can complete the whole group theory of the mechanics of the Coulomb orbits that now is about as complete as you can imagine it should be for the symmetry group U2. And the Coulomb symmetry, the R3 cross R3, really orthogonal or rotational group in 4 dimensions is what this symmetry gets at. So you have 6 generators here, the generators of angular momentum, and then this quantity here, this is a vector too, that's 3 more parameters. So there's 6 parameters for the orthogonal, I should say the 4-dimensional rotational groups. That's all stuff that comes after what we're doing here. Here we're just interested in getting good ways to look at and visualize the orbits, be they ellipses, hyperbolas that are attracted, or hyperbolas that are being repelled. Now we've done the Rutherford scattering analysis in the last lecture. What we're going to do today is study this in a little bit more complicated situation. You think it would be a simpler situation, but here we're going to be actually up close to the nucleus and launching in various directions. The Rutherford was simplified by the fact that the source was at infinity and all of the particles that were coming in were in line with the same speed. That was what gave the Rutherford parabola. Now we're going to generalize that. So before I go on, and make sure that if there are any questions you can think of, just of the basic ideas of what we've covered so far in about 4 lectures for the Coulomb side of this. And this, I think, is the most elegant way to describe it, as I'll show some more of today. So is this so far what you have? And of course, this is where we got to in the very first lecture. This is more of the standard description of conic sections, going back to goodness knows when the idea of a ellipse as an orbit came up. And there's some people that believe that one of the first female mathematicians named Hypatia, who worked in the Alexandrian University / library in Egypt, that she was the first one to conceive of the idea that the orbits, everybody sort of knew about the orbits from the Copernican way of looking at things, but this is before Copernicus, and she conceived of the idea not only of the orbits around the sun, but the idea they might be elliptical. Okay, I don't know if she's responsible for these quantities, epsilon and lambda. I think that came quite a bit later. In any case, for the physicist, here's the Cartesian parameters A and B. This one is really remarkable because it just has energy. It just relates to energy directly. We'll use that again today. So here's the formula for the physical, in this case, invariant quantities, energy and angular momentum for the Coulomb field are invariant. And then the polar parameters, eccentricity. That's a very complicated expression that we've worked out, but it's not so complicated when you look at it in terms of Cartesian. It's just a Pythagorean relation. And then lattice radius, which is only a function of angular momentum, but it is the ratio of b squared over a. So one other thing that is not shown here is time behavior, and I want to make it clear that if the energy behavior is only a function of a, then it turns out you can guarantee that the orbital period will also only be a function of a. It doesn't care about b. That's something the oscillator is not so good at. A and B are needed for both. Okay, let's keep going here. The thing that I want to do is make sure that you see the complete construction again of the eccentricity vector. The idea that you start with some direction you've chosen to throw something from a point P, some distance from the Coulomb center, and that means that you'll be considering throwing it either way, because this is quadratic Hamiltonian symmetric to time reversal. So momentum could be this way or by the same magnitude this way. Presumably you get the same orbit. It's not true if it's hyperbolic and you throw it and it disappears, never comes back. Then you have to throw another one the other way to complete the hyperbola. We'll make a point about that shortly here. But in any case, the direction is the thing that you need to specify with an angle that's measured relative to the radius to the center of the Coulomb field. The first focus of every one of the conic sections that we'll be making, be it an ellipse like this or a hyperbola, which is on the next slide. But idea being then that you copy this, this angle so that you get a thing we call the focus locus, which reminds you that this is a mathematical hocus pocus. At least it looks like that at first. But all along this line are different cases of orbits that will be available for this particular direction and direction of a launch. And the way that's quantified is to simply copy this angle again, or just find another way to get a line perpendicular to the launch. This is the ratio line, the ratio kinetic energy to potential energy, and then its unit value, that is minus one unit value, is where it intersects the circle, in this case the surface of the Earth, if you were imagining launching from this particular planet. That point right there is -1. So you have to study what it means to consider all of these numbers here. What they're all sectioned off into various types of orbits that you can get with this particular launch configuration. And so finally, what you do is you pick a value for the ratio KE over PE, and if you pick a value between 0 and -1, you will be getting an ellipse. Okay, as long as you are strictly between this point and this point, those are singular in the sense. If you're here with 0 ratio, that is, you simply drop the particle, you don't launch it at all, and you don't care about this vector P at all, it doesn't have any length, it's just a dot right there, well then the particle just goes really fast around the corner here and bounces back. And that's essentially what happens in a ground state of a hydrogen atom, if we're thinking classically. And that is, you're talking about the s orbitals, the ones that have no angular momentum at all. S stands for sharp, but that's an old name for a particular type of spectra that you see from the S initial states. You get a sharp spectrum. But this particular falling orbit has a name, and I've forgotten the sort of nice, sounds nice in Dutch, but it means diving orbital, a diving orbit which dives and goes bounce, bounce, like that. That's classically what happens, because it's essentially turning around infinite speed right here and coming back. All this is happening all over the place in the orbital you learn about in quantum mechanics, which is simply has its probability distribution as an exponential. You don't even think about what we're talking about here, but that's something you should think about, because you can make semi-classical approximations for S orbits, a very high quantum number, and it's you know, an interesting, still interesting piece of research. Okay, so once you have specified a particular value, a reasonable value as opposed to this one, or this one where you are at escape velocity, that's where you have exactly the same magnitude of kinetic energy as you had potential energy to start with. That means you're out of here. You have enough to go to infinity. That's what this point is. So these 2 points right here and here are their own kinds of singularities. And then beyond that you get hyperbolas, and we'll get to that fairly shortly here. So just remember this ratio, that's the key thing to this particular construction, of the eccentricity vector, which you have picked just by choosing -3/8. I decided I want to do -3/8. Well, I extended out here to the focus locus, and that's where the focus is for the orbit that has -3/8 for its ratio. So once you have the two foci, well, if you have a piece of string and a thumbtack here and here, you can put a string up there, and then just let the string take you around the orbit. And that's what this paper was about, was making a thing where the string would come out of 2 holes, and you would adjust it, and then you just put a pin in there and very quickly draw the orbit. This is before we had digital computers, you see, so it made kind of a hit for people that had no way to you know, make an ellipse very quickly that had physical meaning of an orbit. In any case, as I vary the eccentricity vector from being 1 down to, and right there is an interesting point where the eccentricity vector is shortest, that is, the eccentricity is lowest, with that right there, and you would get an orbit that was the most nearly circular ellipse. And then they start getting elongated again as you go out here. But they also get bigger, because out here, when I draw the eccentricity vector, I'm not going to hit the focus locus until, you know, off the screen here. And then finally, when I get to this point right here, I'm just not going to hit the focus locus. It's parallel. Okay? So you only have one focus, and what conic section has only one focus? Parabola, right? So then your orbit will be a parabola going to infinity on both sides, depending on which way you throw it. Okay, so that's just to give you in a nutshell what this particular region of this construction gives you. Okay, let's see if I'm leaving anything out here. The focus F and second focus F prime allow final construction of the orbital trajectory. Here it is on an ellipse with that ratio. Okay. Now we're going to follow this up with detailed analytic geometry. I'm going to go through that fairly quickly of this thing if it's just sitting somewhere where you don't have access to some, you know, thing to specify what you would you know, normally find physically important. Here's another case where I've picked +1/2. I tried -3/8 before, but +1/2. Whole different story now. We're talking about making an ellipse, not an ellipse, okay, but a hyperbola that goes along either this direction or that direction at first. Okay, and that hyperbola is right here. Okay, so there, put your head to the side, there's its main axis. That's another thing that we need to look at, is how you build the AB frame. This is obviously A epsilon right now, but what's A? We don't see it anywhere. We have to find a geometrical way to get that. Once we get that, then it's pretty easy to set up and draw point by point the hyperbola that goes through that point. So this focus locus here, you see, now has 2 different regions that we're exploring. First of all, the region for the k greater than 0, that means attractive orbits. Remember, we always write our thing -k/r. and then when k goes negative, well, that's a repulsive orbit, and that's what lives in this region. But in this region, this goes to infinity. This one is rather restricted. This one goes to infinity for the focus locus. Now, all of the focus of the cases where k is less than 0, and that means that we have a repulsive Coulomb, a positive Coulomb potential function, and the energy is absolutely greater than 0 for this one. Here, it's less than 0 until you get to the infinity, and then it ends up way up here. That's something we have to see probably with a better drawing than this one. Okay, let's see if there's anything else I need to say. So, this guy goes right up to there, and when you've gotten to there, your focus is at infinity on this side. Okay. All right, let's see if there's anything else. With an r equal infinity, that means you'd be shooting this thing with infinite speed. So it would just go along that straight line. Okay. We'll come back to that shortly here. This is where we actually prove that this construction is correct, that it does give us the eccentricity vector, which we had simply given to you in a simple proof that showed that it matched the equations of orbit. And while I'm at it, I'm going to move this guy down. So it's matching these equations, basically that equation up there for r equal lambda plus r epsilon cosine phi, or else r equal lambda over 1 minus epsilon cosine phi. That's essentially proving eccentricity construction, or algebraic construction anyway. Okay, so let's just once again go through all of the possibilities for putting an epsilon for a particular value of r, and every time you name r, that's the tip of the epsilon vector, and the orbit that goes with that depends on what side of this particular point you are. Okay, this one's creeping up there. I'm talking about epsilon equal to, well, that one's a half. That's probably a little over 1 right there for that particular vector going up. And then this one right here, this, let me go ahead on this screen here. This one right here is pointing to a point that has r equal infinity. That basically is parallel lines don't meet, except that, lazy 8, right? Okay, now as we turn the corner there, this one, as I said, it goes down and very quickly is pointing at foci that are, in the basement here, and then even below that. And finally, when you get to the point where you're pointing at this point right here, r equal minus 1, you're pointing at the parabolic focus that doesn't exist. It's the only focus for that orbit. We need to, study that a little bit, because there is, from this shoot right here, or that one right there, 2 branches of a parabola that would correspond to this point. Now, that isn't the end of the world for eccentricity vector. Eccentricity vector can go past that point, you see, and when it does, it's pointing to focus way up there. That's the curious thing about this geometry, is all the focal points from this one on are repulsive orbits with E greater than 0. There's both of these things here. I'm sorry, these are attractive orbit. K greater than 0 is attractive. K less than 0 is repulsive, because we're always writing minus K over R for our potential. And that's the problem with doing that, is when you say K greater than 0. Wait a minute, that's repulsive, isn't it? No, not for us, because we have that minus sign. So these are right here, all of the repulsive orbits, all repelling unbound hyperbolas. These are all attracting but unbound hyperbolas. Energy greater than 0. you got to shoot twice to get the whole orbit for that one, as you did for the parabola. So only in this region, to infinity down here, is it an attractive bound ellipse. Okay. So you see some of the power of doing the geometry with this eccentricity vector. You map out quantitatively, but also qualitatively, all the possibilities. And then you proceed to construct them. Okay? Very retro. Going back to 600 BC, Mr. Fayetteville. All right. Let's see if there's anything. So I said this one is up in infinity. This guy here, and then this one. Okay, down here. And then you go further. Okay? So let's do this on both screens. So first of all, there's the diving orbital right there. Okay, that guy right there. And then there's this guy right here that goes for the parabola. And then there's, let's go beyond that, there's this one that hits a focus right here, in this case. But I keep going, you see, to more and more negative values of r, okay, until finally I go to minus infinity values of r. This is just minus 1 here. But as I approach finally minus infinity, then what I'm talking about this way, if I get to r equal minus infinity down this way, then I'm looking at a focus that's way up there, okay? So obviously then I'm talking about an orbit that is our simplest geometrical entity, a straight line. It just goes like that, real fast, right? You either launch it this way, it goes, or you launch it this way with that infinite speed, right? The ratio is infinite. Does this make sense? It takes a while to get your head around this construction. Even as I discovered it, it took me a long time to get all the pieces in order. Okay? So that is what is going on here. Now, this is pictures out of that paper, and the idea was we actually build apparatus that did what turned out to look different than that, but it worked the same. Basically, you had one of those old-fashioned drafting pens, you put ink in it, and sat on an overhead projector, and had these great big overhead projectors. They had a big fan in order to keep things cool. And, you know, it was fun and games before we had what we have now to look at the geometry. Anyway, let's also review a little bit about these. These are formulas that will help you on this little test. The funny mock old-fashioned exam that I'm going to have you do 2 ways. One where you have to get it all done in 2 hours and it makes you sweat or something, but you're not, it's no sweat because you're supposed to do it on the honors principle here, and then redo it with whatever time it takes and being careful with the constructions. The 2 are identical. First sheet, second sheet. And there's lots of graph paper. I'll show you where there's some better graph paper available at the end of this lecture. In any case, lattice radius is kind of a neat relationship here. But so is the minor radius. It has a nice form to it. Now, we've been assuming in these constructions that the circle there, which is represents the surface of the planet that we're launching from the surface, the P point there. We've been assuming that that radius, that's this line right here, is a unit vector. That is, this is unit radius. So be aware that if you all have a unit radius, then this is correct. But you need this little extra r here if you're talking in general. So be aware this is kind of tricky using these conversion formulas to the normal parameters for the Coulomb orbits that is present. You have to have R here that you wouldn't have otherwise. Okay, now this is just showing a little bit of the geometry of the things. I'm going to skip that. That's something that, just to help you see how these ratios come out. This is a nice formula here for B over A. Of course, it has lots of plus and minusing. So let's just take a look at, real quickly, a complete construction here. Basically, I'm out on the middle of nowhere here. This is a piece of blank graph paper. And with a ruler and a compass, a rule and a compass, actually, I'm going to build the orbit for minus 3/8 in detail. And you know, this is one of those things where it's so easy for us to just click on this thing here and watch the orbit go, and I certainly can do that. But let's real quick here go ahead and build the construction. Basically, the instructions for doing this, the idea is that you strike an arc around the point P prime here, and what you've done to get the point P prime is swing the focus up here. So now you have 2A. Okay. And the real idea is to bisect that and some other things so that you get just plain old radius A. And that's really what's going on right there. We're drawing that circle with that radius. And then I can bisect that fairly easily. So there are a couple of circles here you draw, and they automatically bisect what you're interested in. Particularly, I want to bisect the distance between the two foci, which we found so easily by putting our epsilon vector down and just extending it. But where's the middle? Okay. Well, these circles will let you get that fairly quickly. And then you also want to figure out where B is. This is just A. We need the B as well, and that comes out pretty easily. Okay. So now we've got the actual frame of the ellipse, and it's Cartesian, so we can use that old Thales, construction with B and A circles. You remember? The thing you don't have is the graph paper probably isn't lined up with this thing because it's tipped, right? But that's a minor addition. Okay? So very quickly you get the whole orbit that we were pointing at before. And let's just see if our simulations are working at all the way they should. I'm going to go ahead and hit this one and see if we can get it. Yes, there it is. Now, of course, the addition to this shows you all of the stuff. It's actually doing it in time, slowing down at the apogee, right? Small momentum, and then that was a construction that we did. I'm going to go ahead and resume it so it goes around one more time here. Big momentum, and then back down to a reasonable momentum, and then a very small one. And this is not a very eccentric ellipse. Okay, the one I showed you before where we constructed the P was huge. We started with something that was about this big, and then it got a vector that covered the whole screen. So this is very much a difference between the Coulomb orbit and the oscillator orbits, where the momentum is about as well behaved as the coordinate. Here the coordinate gets short while the momentum gets long, and then the coordinate gets long, momentum gets short. That's conservation of angular momentum there, basically, right before your very eyes you see that. And so the idea of the foci that are very close to an ellipse that's not terribly eccentric is, I think, important to notice about Coulomb orbits that live in outer space. Okay, so let's see if there's anything else to say about that. I don't think there is. But now we're going to consider, these are the scales. These are basically R circles, ratio circles, for the attractive Coulomb orbits, okay, which include both ellipses and hyperbolas. Here are the scales for the hyperbolic orbits, which includes the attractive ones and attractive ones actually outside, and the repulsive ones which are inside that. And this region right here is where there isn't much change in the location of the eccentricity vector tip as you make a big change in the orbits. You approach the infinity circle right there. So this is all described. This is why this paper has analog computer in its title. That is the analog, sort of the slide rule of the Coulomb symmetry. So let's look at a typical case, and we were launching like that. This is just the bare bones of that, but we're picking that 1/2 for the ratio here, and that means, of course, we are talking about a repulsive orbit repelled by this center. So this is like a Rutherford one, but this is the general case, an arbitrary position to start from and an arbitrary launch direction. And we're going to take this one off the screen here and try to come back to the original lecture, bring this forward, and we'll look at the orbit that goes with that as well. But let's quickly go through this. This is a bit more complicated. I can bisect this fairly easily, get that, but then bisecting my 2A is really a two-step process, and again involves circles intersecting. Then this is saying what you're bisecting here in each of the steps. So I'll leave you to study that. I am not putting a problem like this on the exam, okay? But, you know, if you're interested in doing this sort of thing for a class sometime in the distant future, here it is, and there's more like it waiting. So you basically swing a radius here, and pretty soon you've got the A circle, and then a little bit more effort produces the B as the chord of the A epsilon circle, and then you're home free. You now have the AB frame and coordinate system that goes with a hyperbola that's going to show up here, and once again its tip is whatever angle thing comes out to be. So launching that, and there's another step here just to make the construction equal. One focus here you draw an A arc, and then from another focus you draw another arc in order to find the intersection points of those two, and those will actually be points that represent the orbit. So it's not too different at this point from the Rutherford construction that we got really easily, because the beam was always horizontal. Every part of the beam was horizontal. So there's a great big arc there, and then we've got another arc that we swing out there to get, by intersection, a point on the orbit. Okay? And while we get the one on the other side, they're symmetric. So you draw the arc all the way across the angle, and these are the asymptotes, remember, are the diagonals of the AB axis. Okay, so there are first 2 points, big deal, all right. But now it's easy to get more. Okay, and it's kind of easy just to see, you know, how little they come off the axis. You know, if you're out here, they're still above the axis, and we need to talk about that later on, because that's going to be some of that logarithmic geometry that these orbits obey. Anyway, here's a whole bunch of orbits that make a thing, and then using these formulas we check if we got the angle right, and here's the protractor that would really help us to make this construction quickly, provided we knew where the 0 was, you see. And as you can see, it's about 1 degree off, this construction, so it's hard to get. We got better accuracy when we were doing Rutherford, but this thing has got that extra turn to it that is hard to manage. Okay, it's getting time here, I think, to look at some of the families of orbits. That's a thing. This is the dial that's with the exam paper. And basically launch elevation angle is right there, and then the range longitude is right there. Those are the one way to state the parameters that we're dealing with. If I was going to be launching either this way or this way, I would have, say, I'm just saying, I would make a 70-degree angle from here. And how do you do that? Well, really what you want is twice that here. Let's see if that's there's the gamma equals 70, there's another gamma equals 70. We already got 70 located on this line right here. Just this little dip angle right here is a 70. And then you get 130 for the one that has the focus. Alpha minus gamma times 2. And alpha is the launch out of the horizon, if this was the planet, and we're sitting here making us the North Pole. That's at 20 degrees there. Subtracted, this is alpha minus 72 times that is 100 degrees, so you should be going through there. So it's very easy to check your geometry when you have two protractors that are fairly accurate. And then you just build the R scale immediately by taking a perpendicular to this. So 2 times alpha, that's 40 degrees, just mark it, okay? So saves you some effort to have the protractor. And then go ahead and see what some of the eccentricity vectors look like for, first of all, attractive orbits, and very first of all, attractive orbits that don't go to infinity. That is, the ellipses all live on eccentricities there. Then it turns into hyperbola beyond that. So this is a good example to see, samples of focal points. And here you can see that they're starting to crowd, and they're going to keep crowding right up to the infinity point. That gap that showed in the slide rule at that point. So this is it's a good example of what are the possibilities here. This one is now showing what we just talked about, all of the topology of the thing. Where are the limits? Where are the points? I'll just go ahead and skip through this fairly quickly. The various focus locus segments are seen there, written at various angles. Okay, that's focus locus for that repelled hyperbola. They all live in this region. And then the attractive ellipse, okay, lives there. The repulsive ellipse, attractive hyperbola live here. The attractive ellipses, foci, live there, and the parabola separates them. Okay, I think that's most of it. Yeah, this is just saying attractive ellipses are all lying on that region. It goes to infinity in lower right-hand side. Let's go ahead and just see the hyperbola is working on our simulation here, the one that we worked so hard to get by geometry. There it is. Just bye-bye. Okay. And if I wanted to screw around a little bit, I would change the sign of the initial conditions and go the other way. But I don't know exactly how to do that.
Just poke minus signs in front of the momentum vector.
Here, right here, without, and then just do a...
Try that.
Put a minus in there. Let's see if it'll work.
You might have to subtract 180 from the bottom. Okay, so it's restricted.
Let me see if I've got minus there. Okay. That looks good. That
all
looks
depends
good.
on how
I was trying to put a
is.
minus in this machine. I got to put it in this one, right? Okay, so let's see if my reset, I got to grab the right cursor, reset should take me to the rest of the hyperbola. Okay, and off she goes, getting very straight. And we've got a time limit on this when you can change that. fix the time limit to anything you want. And obviously, the terminal time right here, you want it to be large if you're talking about things that are elliptical or elliptical families, and that's what this program is really good at doing.
Could you
is making
restart
families.
Restart it one more time. It's so fast. Just reset to 0.
Oh, sure.
I was viewing elsewhere.
I'll just do this.
Yeah.
There we go. And get rid of the minus sign. I think your little toggles here will do that for me. Ah, it won't, but I can always put a 1 in there. That is something we really should fix, so it's really easy to
Putting a 1 in?
put 1 in there, and we'll reset to equals 0. So there we go. Okay. Well, on this side of the picture here, and I've got to go here and make sure I'm back on track. There's those slide rules again, and we're going to mess with the hyperbolic ones in just a bit here. But let's get it running as a slideshow. And these are some more of the stuff that we talked about. But one of the things I want you to notice right here is one of the things that you can do after you've constructed a arrow that is a axis of a particular ellipse. This is the eccentricity vector. It divides always divides an orbit in half, right? So this is a dividing line right here, and you can just go ahead and draw a circle around that thing, and it'll give you some idea, if you make the thing here, of what the orbit would look like if it was just a circle around this focus, if it didn't use this focus at all, okay? But what you're going to get that's right by doing that is the range. So there is going to be an ellipse that's a different shape than this thing, but it's going to end up there.
So ellipse.
So the range by section circled, not an orbit, okay? But it is going to be correct where it hits, if that's where it started. Okay, so that's a nice trick, just to quickly make sure you get your end point right. Then you go for construction of the ellipse using these two foci, prime and secondary. And as we've pointed out a lot already, the secondary focus has nothing physical there. This is the thing that has the physics. If you're talking about, say, orbit around some neutron star or something that's all concentrated in this little dot, there isn't anything here, but it's important for the mathematics of the thing. In any case, by simply taking this vector right here, swinging that from that point, I produce the r prime that goes with this thing. So I get 2a when I'm sorry, am I doing that correct? If I think that's right, from this point and do my r prime, that's this, but strike it here, and then measure the distance. That's giving me the string length, okay? Basic idea is, if this was the old-fashioned, putting a thumbtack here, putting a string out, holding it with my finger, and then bringing the string out to this point, okay? That's, you know, a way to create the ellipse that we're just going to draw by geometry. Here's the actual ellipse, okay? So that range bisection circle goes through the same point, but that's the actual ellipse that has the correct tangent velocity to start with. It's making sense a little bit? Okay. Now you can see why I wanted you to see what it was that we used to do in this class, and that was give exams like the one that you're going to fake the old-fashioned way of taking it first. You had to know this, right? Now you can go back and look at this when you forget what the details are, right? So I'm saying for those first 2 hours, don't do that. See if you can get a lot of this down before you go in there. Now, this one is also interesting. This is the epsilon vector as we make a parabola. So this epsilon is pointing at a focal point at infinity, okay, on this focus locus. Okay, second focus is at infinity down there. All right. Now, something that's interesting about that is if I know parabola has to go through here, okay, it also has to go through here, so I am right in the neighborhood of being able to construct that parabola that's going to be a result of having enough speed on our launch, that's this vector right here, enough speed on our launch to make a parabola that has this as a focus, you see, and then is tipped at 45 degrees to the line parallel to that one, crosses this lattice radius right here, and then goes off yonder, and then the other side of it's going to be coming through right there. And that's telling you, you see, something that's really kind of neat to think about. When you're launching projectiles on the Earth in a Coulomb field, not inside where it's oscillator field, but outside, as you increase this velocity, you get more and more range, just like you do when you're doing the sophomore physics on a planar uniform gravity Earth, okay? More you get down here, more and you get down here. That's essentially your exam, is just to work out what are the possibilities there. And as you see, finally there comes a point where I start to curl around and hit the Earth on this side. And then maybe some more will hit me on this side. Can I keep doing this and go, you know, right around and hit there and finally hit there and finally hit me in the back of the head? Can I do that? The answer is no. Not without changing the angle of your launch. Okay? There is a maximum range for this setup. And it's right there. Okay? So, you can make your parabola go this way, but it isn't going to come back on this line. In order to see that parabola, you've got to take that same speed and launch this way, and it'll go here to infinity. Very different from where that one ends up, right? Very different. I'm using the infinity loosely here. Go 1,000 miles, right? There's many thousand miles between where those two end up. So, you know, this stretches ahead, right? You start to visualize. How many people saw Hidden Figures? Right? The African-American women who did the mathematics for John Glenn to get his first orbit in Virginia. That was where the NASA's comp lab was. The brains of NASA were at Wallops Island, I think it's called. Okay, in Virginia, right? They had to get this visualization. And the other guys, it turns out, didn't have it. They were just using their textbooks to do algebra, but the women had a visualization. One in particular had a way to really visualize what, and they were in deep trouble. I already got Glenn up there, and he was about to burn up because he had something loose and had to take a different configuration. And this was an exam. This is where taking a speed exam really counts, right? You don't have 2 days to do this problem. John's going to die. And with it, the U.S. space program. So that was, if you see that movie, you'd be aware of that amazing thing. Now here's our kite. The kite is in there to help us
What was
see
the title again?
the actual parabola.
Do you recall the title?
Hidden figures. Yeah. And it has all of our social, you know, the fight between the Civil War, right? The Civil War where blacks were slaves. And at Wallops Island, they had different restrooms, right? Colored, white, okay? And so these poor women are doing all their calculations. In this building, the nearest bathroom was like a mile away, which you had to walk through in the rain, okay? Finally, the director of the comp division, and you'll see this in the movie, says, like, screw this. And he went over with a sledgehammer and he took the colored signs and he knocked them all off the wall. This is being political, okay? You got to be aware that sometimes you have to talk back. And that was the end of it. From then on, we're like the real, you know, the European world where we don't discriminate. So that was one of, I think, the most important sociological thing to come up with this movie.
They had problems with
You should
sex
speak
slavery
up.
in Europe.
Pardon?
They have problems with sex slaves in Europe.
And they should end them.
Big time.
They should end them. Yeah. I think we have some in this country too.
Yes.
You know, that should end. Yeah, we've got to end that stuff.
Awareness.
Yeah. Okay. Now, this is just going very quickly through the idea of maybe changing that launch angle, but keeping the speed of launch the same. Okay, so I'm going to orbit with gamma equal 45, and then I'll go up and I'll orbit with gamma 60. Okay, just to see what do I get by doing that. I get a new focus each time. Okay, if I'm going to work off of 60, then I'm going to use this focus instead of that focus. Well, what is it all the foci, plural for focuses, okay, what is it that they share, okay? If I'm launching it at the same speed and the energy depends on A through energy equal K over 2A, right? Then my A value, that's the length of my string, right? The sum of this distance right here to that distance, it's got to be the same as the sum of this one, which is still the same, but this one has also got to be the same, right? So all I have to do if I was, you know, holding that string here is swing an arc. There's where all my foci are. I have a circular focus locus coming up now, okay? That's the idea. All the foci lie on this circle of radius 2a minus this number here, okay? And they're around the launch point. So that's why the analog computer had a bunch of circles to put down the second focus for a given speed. So this particular magnitude of the initial momentum is the same, but we're all putting it in all the different directions. So that's a basic sketch of where the different orbits will be winding up, but more important than that is I'm drawing an extra little line here, and that's the envelope of these orbits. As I go with a particular launch, okay, there will be a particular point where the actual orbit for that touches the envelope circle. And in this case, it's this one right here. And this is what I was talking about when I said that the focus of the orbit and the focus of the envelope have to be on a line. This is the launch point. Have to be on a line, in this case, with the launch point. You'll see more pictures of that coming up here. Now, I'm going to go ahead on this thing and get rid of that particular animation, bring us back and synchronize our, and this is the construction of the ellipse that was just animated. Bang. Okay, and we've got to go through this guy as well. It shows the topology of these orbits. There's the range problem, there's a close-in range problem. But here, what we're talking about are a whole bunch of different orbits that all fit in a particular ellipse. Okay, now this is a much better picture of the orbit and the envelope. Let me get it here where I can reach it and point to it. Okay, so just imagine you're doing this with a string. You've nailed your string here, and it has just exactly the right length to make this orbit. Okay, so you take your pen, stick it inside the string, and draw this one, and 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 come all the way around again. Okay. Now what you've done is at a particular point you have contacted the ellipse that will envelop all of the orbits that are made by the different momenta. So there'll be another orbit that contacts, say, down here, and you have to guarantee that you'll be, when you make this orbit, you follow with this particular string, and as you move the string, it forces you, because this is very short, it forces you to make a turn that a string going to this point right here would not make you do. You would continue up this way right here. You would draw the envelope by putting the string's pivot right there instead of here. I don't know if that makes any sense, but that's the way to think about it. And the same thing with that Rutherford problem. The foci of the orbit has to be on the same line as the foci of the envelope. Now the foci of the envelope for the hyperbolas was a parabola, and it was an infinity, so it has to be on a line that goes to infinity horizontally. That's a little bit of strange topology. This one, much more up front. And that's true when you do envelopes of hyperbolas as well, which we're going to look at shortly here. Okay, so this is the example of old-fashioned graphics of the result of doing all those orbits at once. And this is a good deal more complicated for a number of reasons than the one that we saw with our isotropic harmonic oscillator. In the case of the isotropic harmonic oscillator, you had something that started out a circle and turned into an ellipse, and then rode the outside of the elliptic envelope and then reconverged on the other focus. This is quite a bit more complicated than that. So I'm going to go ahead and see if I can set that up here fairly shortly. Also, I want to take a look at comet heads. Comets come into the sun, feel the solar wind, and make tails, okay? If the comet head is sort of ideal, by that I mean it doesn't have any magnetism that screws up the ions that are involved in these scatterings, it will make a boundary right here, assuming that the ions are distributed Boltzmann-like way, so that there's a maximum that's pretty peaked, which is actually fuzzy. Here we're drawing them very sharply, the boundary here, but with slight variations of velocity that gets fuzzed out a little bit. But what we're talking about is the ideal case of isoenergetic emission from each of the comet heads. And this is just a picture here showing where you would draw circles for the attractive, like the Coulomb attractive orbits, okay? And then here are a bunch of circles that haven't been drawn yet, but they're going to get real crowded up to this point, and then there's going to be some more circles up here, and that's that slide rule scale for the repulsive orbits. But in any case, here's the animation that I'd like to show you. I think we can probably do them on both screens because the color is very different from these two display devices. Let's just see this one first, and then I'm going to try the other one just for the heck of it. But bang, something blows up here. Okay, so it starts out kind of like the isotropic harmonic oscillator ones. It makes a ball, sort of like the volcanoes of Io, right? It starts out circular, but then at some point, the ones on this side have to reach a maximum, turn around and come back. These guys are gaining speed over here and headed, some of them direct collision with the charge, positive charge. These are all positive particles. This is Rutherford scattering from one point, okay? And there they come, they're coming in very bent, and now the computer has to adjust the step size so that it doesn't make a mistake for a couple of those orbits. This is, you know, one of the things that and now it makes a little loop there. I mean, this is way more complicated than the oscillator. Okay. Meanwhile, these guys are sort of reaching their peak. These guys are bouncing, diving orbitals. Okay, there's an s orbital in there. Somehow it made it through the nucleus, right? We're not letting anything be left behind in this particular simulation. Now these guys are sort of reaching their peak and decide they got to go do the same thing these guys did. Isn't that amazing? Just look at that. So when you're in space and you decide you want to have some fireworks or blow up something, boom, okay, it all goes away. And then it comes back. And that's what's going to happen. And already the stuff that you blew up, okay, it's just come by you, right here, if you were here, right? And now, they're all going to have a little tete-a-tete. Look at this. These guys run into those guys. Now, we don't have any repulsions between these particles, so they don't see each other in the simulation, right? Okay, it's time for those guys that turned around so slowly. Remember, that's the thing about the Coulomb, is that the guys that are out there have very little velocity because their angular momentum is made up for by the great distance they are from the charge. So now they're going to take their time turning around. Okay? Meanwhile, these guys are all meeting each other in finding kind of ways. Especially on the line. This is the line between the two foci. Okay. Isn't this wild? Have you ever conceived that this is what happens? Well, it takes the computer to show it. If I wanted to really be mean, I'd have an exam where you draw these guys right where ruler and compass. Right? And you'd show up at midnight, shoot the professor. Okay, so here comes a great denouement of these right here, and the computer's slowing down. This is not real time because we have to adjust the step size in order to make orbits that are, you know, almost micron sized correct in this crossing that's happening here between a large number of particles. And finally we get out, and now you can see what's going to happen next. If you're the guy that played the stunt to blow up a bunch of stuff, right? Puts this junk out in space, right? You're right here. You're going to die. Because it's going to explode inward with exactly the velocity it went out in. Unboom! Right there. Okay? You're beginning to get a feeling for some of the problems we have with space junk. You don't want to blow stuff up in space. Now, admittedly, if the Earth was this big, okay, a lot of these got stopped, right? but there are a lot that didn't. Okay, I think that was fun. This sure surprised me when I first did this. Now here's another picture that I think is worth taking a look at, and this is a burst that's feeling a solar wind. So this is, again, blows up around a repulsive guy, okay? And of course the repulsive guy pushes immediately on these guys, on the particles, and leaves you with essentially a comet head. Now, the question might be a real quick answer. This obviously is an envelope of hyperbolas, but the envelope is hyperbolic as well. And the question is, where do the asymptotes meet? There's an asymptote there, and there's an asymptote there. Does it meet here? No way. It's exactly halfway. So that's a cool lesson also. Okay, so let's go back here and take a look at some more of this. This one I think is cool because it's Rutherford scattering from a point. Now here's the beam source, right? Go ahead and run it. Kaboom! That's kind of like what we had with Rutherford, except it's more extreme in terms of the angles that are present. Okay. So there's where it stops. Now, when you run this, you don't have to stop the thing. You can let it go, let it finish. And I can do the same thing with the other one. Let's just watch this one for the heck of it. Look at those things going down there and out there. And there's a very sharp line right there, which you can draw up and see where it crosses. Is it really at a half or not? You should try that. And the same thing with this one over here. Sorry, wrong mouse. Resume here and just let it go and make really straight lines. Kind of already at the edge of the drawing already, but it's worth going the other way. You can always slide these things over and change the position of the point on that is the charge. Okay, now I'm going to make a point of pausing both of these because they do go forever, and that's computer time taken away from other exhibitions. In any case, let's go back to this. I'll let that one there for a while. This I think is cool. Is that with the right boil-off of velocity on a comet, you'd get a flat comet. This is a flat-headed comet. Now we're not probably going to see anything like that because, you know, think of the distances we're talking about. But in some other situation, a plasma or something, something like this could occur. So low energy, and I make that thing high energy, and I make something that goes like that and wraps it in between those two as a case of a flat comet. Okay, flat envelope, I should say. All right. Okay, now the rest of this is fairly simple. I probably should leave it to you to read, but I just want you to see, problem. Find trajectory angle of minimum energy to fly from start to 90 degrees longitude. Okay, what's the, minimum? So you'll go calculate it with algebra and stuff. You take a lot of time. Here, it's really very simple. You know where the other focus has to be halfway, okay? And then you just find the minimum circle that touches that one, okay? That has the other focus, that the ellipse that you will be drawing. There's the R thing. There's the actual values. The eccentricity has to be right there, okay, in the diagram. And then this is another question for a different thing. This is with long triangle 22.55 maximum range of trajectory. This is 22.5. But then this is with higher value of this. This is taking it out to here, making a greater range. Okay, and once again, this one shows where your max is. Okay, maximum range is 269.9999999. You actually would make it on this giant ellipse. It goes, oh my gosh, so far out there, and then comes back right to here, okay, after 1,000 years or a million years or something, okay. But if you just shoot that thing with a tiny bit more speed, it doesn't come back. That's really cool. But of course, it takes a long time not to come back, because it gets out there and slowly, like Halley's Comet spends years, eons doing its thing. Okay. And then this one, I find this one to be sort of fun. This used to be a good exam problem in this class. Okay. Was in sophomore physics, you know that 45 degrees is your optimum launch angle, but that's only true when you're only going a little distance with your throw, okay? You're only going to throw at 5 pixels here. 45 is what I want. But all other ranges, you know, up to here, 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 and here on this globe, okay, completely different angle. And this is just doing the geometry to figure out what that is. So for low range, this is true. The angle theta, okay, is pretty nearly equal to pi over 4, but it's pi over 4 minus rho over 4, okay, is the actual angle. And the other thing is, when we took a look at the optimum throw here, that's what this is. This is one optimal focus, where you have your focus locus circle just touching at one point. Here, the focus locus circle for a bigger thing touches the axis here, a high point and a low point. One of those orbits, this one, goes directly to the target. The other one, and this is, remember, a solution to the quadratic equation in sophomore physics, but it's a little more complicated here. A high orbit goes and also hits the target. There, it's just one orbit, okay, for this. So higher V allows 2 elliptic paths to target. Here, just one. It's the optimal one. So the 2 foci have come together at a particular point. All right, I think that's about it. The rest of this lecture are pieces of paper that help you with the exam. So you can always access this, and that's probably the one that works the best right there, because it takes up the whole 8 by 10 page. And you already have a couple of these, but this one has a better grid. Okay, that's it for now. We'll be taking rotations on Thursday with all sorts of weird shenanigans involving that thing and a couple of other demonstrations.